So how do we actually find solutions to a second-order differential equation? Well, we have to consider it by cases, and a very special but very common case is what's called a second-order constant coefficient differential equation. So anything that's in front of the function or its derivatives will be constant. Y double prime minus y prime minus 2y is 0. That is an example of a constant coefficient differential equation. And so the idea is that the solutions are always going to be of the form y is e to the lambda t. We found that y1 was e to the 2t and y2 was e to the minus t. We also found that the Wronskian of those two solutions ended up being non-zero. So they are linearly independent. And by the previous result, which I'm going to call as theorem 2.1.3, the general solution is then going to be a linear combination of these two answers. So every solution to this second-order differential equation comes from this linear combination. That's it. That's the whole process. In general, when I've got a second-order constant coefficient problem like this, and then I let y equal e to the lambda t, it's going to end up giving me a an algebraic equation that looks like this. I know that's never going to be 0, so I'm going to end up with basically a quadratic equation. This is called the characteristic equation. And I have to solve this to find the lambdas. Now, way back when, you learn how to solve quadratic equations. From the quadratic formula, this is going to be negative b plus or minus b squared minus 4ac all over 2a. You have to be a little bit careful, and you need to consider this thing here. This is called the discriminant, and there are some cases. If this thing b squared minus 4ac is positive, you get two real valued distinct roots. If this discriminant is b squared minus 4ac and it's 0, you only get one solution to this problem, but it's repeated. And if b squared minus 4ac is negative, then you'll get what are called complex solutions. Now, complex solutions will be discussed in another video, but for now we'll talk about these two cases. Well, we've already seen what happens for real distinct lambda. You're going to get two solutions, e to the lambda 1t, e to the lambda 2t. The Wronskian of these things will always be non-zero. It's very easy to check this just by using the chain rule. And because of that, you will be able to find that this will always give you lambda 2 minus lambda 1, e to the lambda 1 plus lambda 2 t. This thing will not be 0 because they are distinct. So the general solution will always be c1 e to the lambda 1t plus c2 e to the lambda 2t. What if I have a repeated solution? So for example, if I have this equation, 9y double prime plus 6y prime plus y is equal to 0. If I use y is e to the lambda t and I sub this back in, it's going to get 9 lambda squared plus 6 lambda plus 1 is 0. Now you hopefully will be able to show and factor this, and you'll get 3 lambda plus 1 squared. And this is going to tell you that you've got lambda is negative 1/3 as a repeated root. So I know that one solution will certainly be e to the minus t over 3. What's the other solution? I know that it must exist by my previous results. From that theorem 2.1.2, the uniqueness, I know I have to have two linearly independent solutions. We know that if lambda 1 and lambda 2 are not equal, then any linear combination of them has to be an answer. So this linear combination will be an answer. And that means that if I call this thing u, another way to write u would be e to the lambda 1t minus e to the lambda 2t divided by this stuff. And because they're distinct, then that will never be 0. So what do I want to do? Well, I want to check to see what happens in the limit as lambda 1 gets closer to lambda 2. If I take the limit of this quantity, I want to see what happens to it. If I were to sneak a peek with this limit, I'll find that it will give me 0 over 0. So if I use L'Hopital's rule, when I go through and I apply L'Hopital's rule, and I take a derivative with respect to lambda 1 of both of these things, I'll end up with the following result. T e to the lambda t should be a solution. Now, I'd have to check to make sure that this satisfies the differential equation. So you can check for yourself that it does satisfy the DE. Now, in our particular case, when I have 9y double prime plus 6y prime plus y is equal to 0, if I were to take t e to the lambda t, e to the negative t over 3, if I were to take its derivative and use the product rule, I'd get e to the minus t over 3 over 3, e to the t over 3, and then I'd have to differentiate it again, which I'm getting lazy to do. You can show that the left-hand side equals the right-hand side. In the case of a repeated lambda, e to the lambda t, t e to the lambda t will be the basis. And again, you can check that the Wronskian is non-zero. And all you need to do for that is just plug it into the Wronskian, take the appropriate derivatives, and show that they are non-zero. So that'll work well. So in this final example here that I want to go through, I want to now show you how to deal with an initial value problem. So if I were to give you the DE with these initial conditions, we go e to the lambda t, we would find that 9 lambda squared, 6 lambda plus 1 is 0. Lambda would be negative 1/3. Negative 1/3, it's a repeated root. So y1 is going to give us e to the t over 3. y2 is going to be t e to the negative t over 3. The general solution would be c1 e to the negative t over 3, c2 t e to the negative t over 3. That's what we're going to call y. In order to satisfy the initial conditions, I'm going to have to differentiate this. So c1 over 3, e to the t over 3, c2, 1 times e to the negative t over 3, minus t over 3, e to the negative t over 3. So that's me just differentiating this. And if I were to put in the initial conditions, y of 0 is going to give me c1 plus 0 is going to be 3. So that means c1 is 3. And y prime of 0 is going to be negative c1 over 3 plus c2, 1 minus 0. And that has to be 0. So if I put this all together, c2 is going to be c1 over 3. And that means c2 is going to be 1. So the solution to the initial value problem is 3 e to the negative t over 3 plus t e to the negative t over 3. That is the one and only one answer to this problem that satisfies both the differential equations and the initial conditions.